So I just wanted to pick up from where we left yesterday. If you remember, we gave a general introduction to how we can put the different kind of colliders on the map in terms of the center of mass energy and their luminosity and what they can do. And we reviewed some of the past, and we focused quite a bit on the present, which is the LHC, and the close future, which is the high luminosity LHC. And I gave you reasons to emphasize the importance of that physics program. And then we started looking at where to go from here. I didn't show you anything about that, so I did not already present which kind of ideas are out there and what the future have reserves for us, hopefully. But we started discussing what are the principles that we followed in order to propose one or the other direction or both. And I want to pick up from there because we had a discussion towards the end, and then by talking to some of you, I think that one of the things that I said was not clear. So I remember your question, for instance, and then talking to people afterwards, I realized where the misunderstanding was probably. So let's start from there again, and add to that, and then move on from there to see the scenarios of different possibilities that we have. So. Remember that the discussion that we were having was just how do we go from here? So we have the LHC that can explore certain regions in energies, right? And can reach a certain level of precisions. And where do we go from there? And I was saying we have both the possibility of direct detection of new physics, we have the possibility of indirect detection of new physics. So we can either push the energy or push the precision of the machine. And in both cases, it will not be identifying a machine just because it does only that, but it will be just the main characteristics of the machine. And the discussion that we were having was on this kind of oversimplified representation of theories beyond the standard model that I was having in terms of just the theories that somehow live at a certain mass scale. So they are identified by a mass scale that let's call is MBSM, or you can call it the mass of new physics. And they couple to the standard model through a generic coupling that may not be exactly that, but is related to that. If you think all the different possible kind of electroweak interactions that you have, they're all proportional to an electroweak coupling with different prefactors. All the different QCD interactions that you have, they're all proportional to GS with some prefactors, and the same for new physics. So in a very hyper simplified way, I should assume that the coupling is a certain coupling of GBSM, which is the coupling of these two-dimensional parameter space of your BSM theory, right? So this plot had precisely that on the axis. So it was the two-dimensional parameter space. And I was saying the LHC lives here, let's say. Where do we go from here? Now, what was probably not clear, and probably it's just me not having said that, is just that what I have in mind here are just direct searches, okay? So direct searches, and let's write it in a different color, maybe too many, all right, here. Clearly, the LHC is limited in mass and also in the range of couplings that it can explore by direct searches. And what that means is just that I assume that something has been seen. So if you see something, what you can see, not what you can exclude, but what you can see, that I think was a misunderstanding. So not what you can exclude, but what you can see at the LHC is limited. right? Because for a given value of the mass, you can explore a certain range of parameter, or for a given range of parameter, value of the parameter, you can explore a certain range in masses. It's different if you now take the same plot and you say what I can exclude at the LHC. Then, and that was the confusion. I say if I have a lower bound from there up, because I increase the coupling for a given value of the mass, I can exclude all the couplings from there on. But if I see something, what I'm saying here is what I can see at the LHC is a region in this parameter space, okay? Now, if I'm now thinking to extending the capability of direct searches to see something, I can extend both with machines that have cleaner environments, and therefore they're able to see things that are not higher in energies, but they're weaker in couplings. And so they may have escaped the LHC because we don't have the sensitivity to really see these couplings due to large backgrounds, less capability of the machine to really see through the fog of whatever else is there. Or we can extend towards a higher mass scale if we have more energy. And of course, as I was saying, yes, there is a spectrum in between, right? So some of these machines, they will not only extend in energy, but they also reach weaker couplings. And some of the machines that can go to weaker couplings can also push a little bit the energy with respect to the LHC if they have enough energy in the center of mass. So if there are lepton colliders, typically that can be pushed in the center of mass energy to beyond a few hundred GeVs. So when they can get to the 1 to 2 to 3 TeV, if it's a muon collider, it can go even higher than that, but then it belongs to the other family. So that was the meaning of extending things in this direction, right? Now my drawing may not be spectacular, or in this direction. So it will include the LHC, but it will go to higher energies. So in this direction, you need higher energy. And in this direction, you will get higher precision. So in terms of what we learned yesterday, you need higher luminosity, right? So this is where luminosity means also that you have a cleaner environment available to you, and that contributes to the higher luminosity of the machine. And so these are the two main directions in which you will see, as soon as we look at the specific names of the future colliders that are under discussion, you will see them divided, if you want, into two main groups. The ones that still live at relatively low energies, but are lepton colliders, typically plus and minus colliders, and they really reach higher levels of luminosity, and the ones that push the energy. And so we call them, and this is an interesting point, we call them, in the first case, so in the blue case that we have here, we call them Higgs factories. And I'll comment on these. Probably I shouldn't. Let me just write HF in here. And then this is what stays for Higgs factories. And the other one, since they push the energy, so whatever lives in here, we call them a multi-TeV collider. So as you will see, among the Higgs factories, I could write here E plus E minus, because they're all E plus E minus machines. And among the multi-TeV colliders, there is a mixture, right? So there are colliders that are PP collider, like the LHC, but at much higher energy. There is the newcomer that we briefly mentioned yesterday, the mu plus mu minus collider, the muon collider. Some of the E plus E minus machines can be pushed to higher energy, and we having to choose an arbitrary threshold where to make the distinction between the two, we picked 1 TeV, and this is something that a schematization of colliders that came up during the community workshop that was cited yesterday. This is no mass community workshop, but has been also the common language for in other similar kind of exercises, if you want. So put the kind of the threshold between the two around 1 TeV. So everything that is above 1 TeV is considered to have higher energy in the center of mass, so multi-TeV collider. And anything that is at or below the 1 TeV is considered to be Higgs factor, right? So this, and this is why here I will put also E plus E minus, because we have some of the proposal for E plus E minus, the energy of which can be upgraded to higher values, right? Or start even to higher values. Some of them are circular colliders, some of them are linear colliders in the case of E plus E minus, while for the other two categories, they're all circular colliders. And we discussed yesterday what's the difference between the two in terms of when to go for one and when to go for the other. Now, as I said, I wanted to comment about a little bit about this name, right? Also because the real thing, as I said yesterday, the discussion that we started yesterday was really why collider physics, right? So to give a motivation. And why do we call this machine Higgs factories? Why we are putting so much emphasis on that? They're not only producing Higgses, right? They're producing a large statistics of all the standard model particles. So they're producing, as you will see, billions of Z's and W's, even not all of them. As I told you yesterday, I wouldn't say top here, and the reason for that is just that they're limited in energy, and so unless you go to some higher version of them, you don't produce as much as the LHC, which was one of the things that I told you. Just remember that the LHC is pretty unique from that point of view, and whatever top result will come out of the LHC will stay with us for a long time, right, before it's passed. But why Higgs factories is because that is the main emphasis. This is one of the main leads and reasons why to go beyond the LHC, right? So why to imagine or if you want support the need of something beyond the LHC. And so the two main, if you wanted, the two main reasons why we wanted to go beyond the LHC is really, on one side, so when we go to higher energies, the reason is obvious, right? It's just to explore the next threshold of energy. And several beyond the standard model hypotheses, plus some general principles that you may or may not subscribe, but they tend to point to the not only need, but likeliness that between 1 and 10 TeV, so around the 10 TeV scale, we'll find the new physics, around or below or a little bit above that. So exploring the 10 TeV scale is really, really important. So why to go to higher energies? This is just one of the two main, in going beyond the LHC. One of the obvious reason is just to push the energy. And so explore, and let me write it in red, just to go with the color that I used there. So to explore the, say, 10 TeV scale. And for that, you need, as we learned yesterday, center of mass energy that is clearly past the 13, 14 TeV center of mass energy of the LHC. You needed to go up to tens of TeV. So the ballpark number of 100 TeV that you will see in the table that I will show is just symbolizes that, right? So this, I don't think it requires any more words, right? The other one, so the one that pushes us to call this object Higgs factory is really to explore, I will say the Higgs, but it's not the Higgs by itself, it's just what the Higgs represents. And so let me call it explore Higgs physics. But not just because we wanted to know its coupling more precisely, because we always wanted to know things more precisely. These machines will also reach, as you will hear probably in your lectures on the standard model, they will reach an incredible level of precision for all standard model parameters. So for all the standard model traditional things that we measure in electroweak precision fit, they will pass the current precision by at least 1 order of magnitude. And this is something that we want to do, because it's not just to discover new physics, but also to set our base ground on a super solid base. So saying this is what we know for sure about the standard model. This is really important. But it's not just that. It's just that the Higgs sector of the standard model, the scalar sector of the standard model, we believe, and maybe we not all agree on everything, but I think it's pretty clear that it is the most uncertain and most unsatisfactory sector of the standard model for many different reasons. right? And let's try to summarize briefly some of them. So, and it's the one that we know the least at the moment. I told you what the LHC could do, so reach couplings, measurement of couplings at the level of 10, 15, between 10 and 20%. But high luminosity LHC will go below that. We want to really to reach and lepton colliders, so these Higgs factories, we really reach the percent level and below the percent level on some of them. So, but why do we really want that? It's just because, so there are the scalar sector of the standard model, I think has two main parts, right? One part is the one that couples the Higgs to the gauge structure of the standard model, which is where the spontaneous breaking of the electroweak symmetry is realized. So one part that I would call L scalar is the one in which you have the mu phi dagger, the mu phi piece, where here you have the coupling to the gauge boson. And also the origin of the mass of the Higgs in here, right? And then this is the potential part. So this part is kind of pretty solid, I would say, meaning that if you have a scalar theory and you want to gauge it, this is the only way to do it. And it's the only way to introduce naturally the first step towards then messing up thing with the potential that you introduce here that makes it not a traditional Klein-Gordon theory, but a Klein-Gordon theory with the wrong mass sign. Why is that? So this is the real part on which we should have a big question mark. Because it works, but why it works, and why it's like that? Why it works, we know why it works, but why it's like that, we don't know why it's like that. And so the big effort here in measuring what we call the triple coupling of the quartic coupling of the Higgs is fundamental. And when you think, when you hear talking about the lambda coupling, the surf coupling of the Higgs, which normally many times is the only thing that people talk about, you should also remember that there is not just one. There are two. There is one in the standard model, but technically you have a triple coupling and a quartic coupling. So you have the coupling where three Higgs come together. And I'm here talking already post spontaneous symmetry breaking. So this phi is the full doublet, right? It is the one that upon spontaneous symmetry breaking goes into the doublet in which the Higgs lives, which is here, and this is the vacuum expectation value of the field. So in terms of the physical field, the H field that comes out of the doublet, you can couple 3 of them, you can couple 4 of them. And in the standard model, they are the same, but we need to test that, right? So this is the first thing that is really a mystery in a way for us, right? Now, the other thing that is the other place where the Higgs comes, the scalar field of the standard model comes into the game, is the Yukawa part of the Lagrangian, so the coupling to fermions. And the coupling to fermions, well, in terms of standard model field, let me write it in terms of there is a part that couples the U-type quarks that has the phi twiddle, the I sigma 2. You will see this in your lectures if you haven't seen it already, times UR. And then there is a part that couples the down-type quarks. And the same would be for leptons, except that if I include neutrinos, if I do not include neutrinos, I have only a piece of them. If I include also the neutrinos, and I'm going a little step beyond the standard model if you want to have both of them. But let's write it for quarks. So you have a coupling of this kind, right? Now, these matrices here have indices. It's an IJ, 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 and they are completely arbitrary. So these objects here are completely arbitrary in the standard model. But they're very, very part of, they also connect different sectors of the standard model, because the moment in which, the moment in which you specify your phi field to the vacuum, and you plug the vacuum structure into your Lagrangian, one term will generate the coupling of the Higgs to fermions, the other term, the vacuum expectation value, will generate the mass of these objects, or a mass matrix to start with, that you then diagonalize and obtain mass parameters for the quarks that are indeed proportional to their respective diagonal Yukawa couplings. However, the standard model has other parts with fermions. And the other parts with fermions are the gauge part, or if you want, the psi part, in which you couple quarks. So the Dirac part, which is the psi bar ID slash psi, in which, from which, by the time you specify your psi to, let's say, Q left-handed and right-handed fields, in here you would have the coupling between the gauge boson, the W and the Z, and the quarks of your model. And U right, and D right, U right, and D right. And actually, the right part of it is here only because you have a photon, right? Because the other two couple only to the left-handed. But so when you diagonalize the mass matrix, so the matrix that here pick up the vacuum expectation value and multiply by the Q bar left I URJ, and you diagonalize this matrix, the diagonalization rotates these quarks in the fermion part of the story, and it gives origin to the famous coupling for the parts of the Lagrangian. They couple up and downs that are rotated independently, because here you have two terms. So you have, if you want, a left rotation matrix to the mass basis, and a up and a U left down, as well as you have a U right down and a U right up. And so when you rotate those to diagonalize the Yukawa couplings, you also have to rotate objects here. But when you pick up the W coupling, this W will put together U bar left and D bar left. And so in here, when these objects go to the mass basis, you will have two matrices coming out that are the rotation of the left up quark dagger and the rotation of the left down quark. That is nothing else that the CKM matrix, what we call the CKM matrix. So this is what gives origin in the standard model to the couple of the W to up and down quark. Here in the vertex, you have this matrix. You have an element of this matrix that you normally call the Vij. And it's the product, really, of the rotation matrix of the up quark and down quark when you diagonalize the mass matrix in the Yukawa. So this is just to say, a long story, to say that, but an important one, because most of the time we tend to think of flavor physics, which is here, and all the nice anomalies that are coming around from flavor physics, as something that has nothing to do with the scalar sector of the standard model, but they're intimately related one to the other. So understanding the scalar sector of the standard model, I don't want to say that it's the same thing as explaining everything that we see in flavor physics, but they're part of the same story. And so the fact that this sector of the standard model is so unsatisfactory from a theoretical point of view, so from the point of view of really knowing why things are the way they are they dictated by a symmetry principle? Are they dictated by the structure of a theory that naturally generates a hierarchy of fermion masses that is unbelievable, so, and completely unexplained? And at the same, it's something that connects directly to another phenomenological field of our science, which is the field of flavor physics. And so now that information and precision measurements are coming from all these different fields, this could all be part of the same understanding. So could all be part of understanding physics beyond the standard model using everything we have. Now, so the message here has been, why do we emphasize so much the fact that these machines will be able to produce a lot of Higgses and therefore do precision physics for the Higgs? It's just because we really want to understand more about. And you have heard in many other different discussions, even during the lectures that you're following here, how the Higgs plays an important role together with other particles of the Standard Model in understanding big problems, right? So let's start to understand what it is from where it comes in, which is really here. So having a lot of them, we can precisely measure its couplings, not only its mass, that is already quite precisely measured but can be improved, but its couplings. And so we can measure with indirect measurement. This will be evidence of new physics through indirect. So if you want, it will be indirect evidence of new physics. What that means is just that we are not going to produce it, but we're going to see the effects of it on the Standard Model, quote unquote, the Standard Model properties. So properties of particles of the Standard Model. So talking about to complete this picture, since we are now measuring the presence of, the importance also of indirect measurement, so from here, we will expect direct searches, while here will mainly be indirect evidence. And it's understood of new physics, right? So how do we sort of map or morph, if you want, this plot into another one in which we take into account both direct and indirect searches at the same time? So we can still use the same two axes. So we can still use our G two-dimensional parameter space for a generic BSM theory. And now say, how can we illustrate in here now the complementarity between direct and indirect searches when we do not really see anything new? Here was just, we have seen something. What can they see? What can these machines see? Here is, what can this machine, if you want, exclude? If we don't see anything. So the complementarity at this point between a direct and indirect measurement. So in a plot like this one, if we have a machine at a given energy, this set a bound. So I can explore up to that energy. And this is easy to set. So these machines are at lower energy, we said above, indicatively below 1 TeV. And then we know where the LHC is, and these are machines that are in the 10th of TeV kind of regime or similar. So if I have to put bounds in here, so if I don't see anything, I can explore with a Higgs factor is something like up to here. I can explore with the LHC something a little, I'm not in scale, right? I'm not drawing in scale. I can explore something, let's say, up to here. And as we said, the LHC will go, let's say, up to here. In the GBSM, the Higgs factories can go lower than that. And the multi-TeV machines can explore higher energies and maybe do a little bit better even on the couplings of the machines, right? So these are just vertical exclusion lines in this plot. You can explore up to there. Now we bring in indirect evidence. Indirect evidence is just saying, I'm measuring a Standard Model parameter, Standard Model coupling, a Standard Model, let's say. Let's call it, I don't know, G, Standard Model. And now, these are, or in general, let's say, I don't want to specify necessarily to a coupling. Let's call it just an observable that you measure. You have, for an observable eta, a generic observable, you measure it, and you see that this observable has the Standard Model value plus some delta. And you call this delta a delta eta BSM, because it's not explained by the Standard Model. Now, this delta eta will be proportional to your two parameters. So most likely, this delta eta BSM will be proportional to the coupling, probably square, because it's coming from a measurement of a rate or a cross-section, and will be inversely proportional to the mass of the BSM theory, also square, right? Because it's coming in as a mediator in your processes, right? So most likely, this will be the kind of effect that you have. So if you want a relation among the two, so you have a relation between the couplings, so it will give in the generic case, it will give you, it will cut out, it will just draw a kind of a swat in this space above which you exclude and below which you do not, right? So the presence of indirect constraints will cut lines through this space that are of this kind, right? And how much you will exclude of this space depend on your precision. Because what your precision is the sensitivity to this delta. So if you can measure and calculate this delta to 1%, you can, it means that you are sensitive to 1% effects. If you can measure it at a lower precision, you are sensitive to something that can have either a weaker coupling or a higher mass, or a compromise between the two. So you will be able to exclude, in the case, more of this parameter space. So clearly, precision, if you want, to bring you from excluding less to excluding more. Now, you can go from here to here, also depending on the kind of, so this is, will be, if you want a BSM, excluding a BSM effect at the level of, let's say, 1%, and this would be excluding a BSM effect at the level of 0.1%, and so on and so forth, right? So the precision of these machines is really what makes you move in this space, and at this point, exclude the theories or do not exclude the theories, depending of course, of the nature of the theory. It's a very general picture. And then you can tell me, well, but the theories can be very different. Theories can have coupling to the standard model at 3 level. Theories can have coupling of the standard model at higher orders. And immediately that suppresses the kind of coupling that you have. So even when you find an exclusion, it's an exclusion that if you specify a model, can tell you a lot about that model. If you do not specify a model, can tell you a little bit less. But then you can explore different possibilities depending on what else is coming to you from other information that can come from flavor physics, information that can come from astrophysics, information that can come from dark matter searches, for a lot of other things that you can put together to build the full picture. But this is just the effect of what going up in energy and going up in precision will give you. So, last thing that I want to say is just, for what concern the exploring the Higgs physics part of the story, we said this is very, there are these two parts that are kind of not so satisfactory in the scalar sector of the standard model. And there is one thing in particular that relates, if you want, the two different directions in which we want to go. So they relate the unsatisfactoriness of the Higgs sector of the standard model to the fact that we wanted to explore the 10 TeV scale. And this is precisely related to the mass of the Higgs, to the value of the mass of the Higgs, right? So you may want, if you want, you can call this the naturalness problem. But it's the fact that the mass of the Higgs is what it is, that the mass of the Higgs is at the electroweak scale. And if you wanted to push it even beyond this, it's really justifying the electroweak scale itself. So justifying what the electroweak scale is around 100, 200 GeV, right? Which is then the value also of the mass of the Higgs. But in terms of the mass of the Higgs, this is pretty evident, and it's pretty nice to see. And it's probably a matter of debate, if you want, meaning that you may accept it or not, that it is like this and not be particularly perturbed by it. But theoretically, there is an interesting point to consider, and it's something that at the beginning I haven't mentioned that I've submitted for posting the notes of yesterday's lecture and part of today as well. So in there, you will see a homework. You will see many little things in red that are little suggested do it yourself, right? And some of them are just check this, check that, make sure that you understand this number, make sure that you understand that number. But one of the things that you will see at the end of yesterday's lecture, the discussion that we started in yesterday's lecture, apart from everything that we have seen here, is just to explore the difference between the higher order quantum corrections to the mass of a scalar and the mass of a fermion. And this is kind of very instructive because what you will see, so it's really what shows to you why the mass of the Higgs is so annoying in a way. And the reason why it is just because and it's important to clarify this point because very often, just talking to students, to young people, I have the impression that there is confusions in there, right? So the problem with the mass of scalars is just that they can receive large corrections. I heard many times saying, well, you can push the cutoff to infinity. No, it's not really like that because we know that the standard model is renormalizable, right? So the mass of scalars in the standard model are finite, right? They're not infinite, right? What it is true is just that it is unprotected from larger corrections. So if any quantum effect that is mediated by a fermion or a vector boson or a scalar, another scalar of extended theory that goes into perturb the propagation of the Higgs will leave a larger correction. So what the exercise that I've given to you is the following one. I think this is how I phrased it. Yeah, so if you consider a theory that is just a theory made of a scalar and a fermion field, right? So you don't need to introduce gauge fields here. It's just a scalar and a fermion field. You can realize this yourself. So you just have if you want the Lagrangian of, so you have the Klein-Gordon Lagrangian, and then you can put in also the terms that introduce the phi to the fourth theory. So let us write it. If it's you can use a complex field if you like. And this would be the mass of the scalar. And then you have your quartic interaction. And I'm already reasoning in terms of the Higgs field. So in terms of the field that has legitimate mass terms with the right sign and a phi to the fourth interaction, just to simplify our life. And then you put in the fermionic part. So you put in the Dirac Lagrangian for your psi field. And then an interaction between the two that is a Yukawa type. So put in, let me write it because I wanted to introduce also the mass of the fermion. And then you put in the interaction between the two, so there will be a G Yukawa, if you want, between the two. That simply I write it like that, right? Now you do the one loop corrections to the propagators of the scalar and the fermion, and you derive the mass parameter, the renormalized mass parameter from there, right? So the mass parameter that you see in your Lagrangian, this will be your zero mass, your bare mass, same here and same here. And these will be your bare couplings. But what we are focusing on the mass parameter here, right? Now, if you now calculate the correction to the scalar propagator, what I mean is just to calculate it at one loop. I use dashed line for the scalar. This would be the tree-level one. And then you would have correction at one loop that are both due to the surf interaction, which is this one, and to the interaction with the fermion. This one, right? And then you have higher orders. And then you do the same for the fermion that I draw with the solid line. And so you have these plus the corrections that are due to the exchange of a scalar. And the interesting thing that you see, so in order to do this calculation, you pick the regularization that you like. I would normally suggest to do it in dimensional regularization, which is easier, so to work in d equal 4 minus epsilon or 4 minus 2 epsilon, and calculate the little loop integrals that you have to calculate here and there and there. But what you will see is just that in both cases, when you go and calculate so let's see if I'll give you a little bit more of details to be fair, right? So because you may have seen it or you may not have seen it in some previous calculation in some of your classes, right? So when you calculate the difference between the delta m square for the scalar as the difference between the renormalized mass square and did I call it m0? Yes. This one will look, depending on what you're using, it will look either something that has poles in 1 over epsilon and or logs of the cutoff, depending if you're using a cutoff regularization or not. So in the case in which you're using dimensional regularization, this will probably look like a coefficient over epsilon plus some finite term. And in the other case, just by power counting, it will look like, let me call B this coefficient. It will look like a term that is quadratic in the cutoff, then a term that has a log of the cutoff, and then some finite term that I call phi prime. So it doesn't matter which way you go, this is the structure. And then renormalization, because the theory is renormalizable, will allow you to, given your choice of subtraction schema that you want to choose, to just come to a finite expression for your mass, such that your mass renormalizable, that is the one that is surviving from here, will be just the ms0 that you have inside plus some finite term, right? Now, if you do the same for the mass of the fermion that enters in the Lagrangian as a linear term from the term that you have there, you will see that the mass of the fermion, a difference from the mass of the scalar, has still a divergent structure. So if you now represent these as in the same way, but it will still have a divergent structure like this one. So in one case, you still have with the difference that you don't have the quadratic term here, but you have only the logarithmic term. So you see it better with the cutoff than not with dimensional regularization. But let me call like prime this coefficient. It will still be of this kind. And it will be as a B1 prime, the log of lambda squared plus finite in the case of a cutoff. And so by renormalization, the mass of the fermion will be equal to the bare mass that you have that multiplies at that point some function, which is what I call it finite. So it will be a function of the renormalized mass and the renormalized couplings. Right? And so the big difference here is really this multiplicative versus additive behavior that you have in such a way that while in this case, this mass can receive large contributions that are brought in by functions that are functions, quadratic function of the masses of the particles that go in the loop, in this case it's multiplicative. And if you start with a theory, just to give you the extreme example, if you start with a theory that has a zero mass, so with a massless theory, you cannot make that that fermionic theory massive. But you can you can change it to an arbitrary value, the value of the mass of a scalar, even in a renormalized theory. So what this example will show you in looking at the difference between the mass of a scalar and the mass of a fermion is precisely the fact that, and you know why this is happening because the mass of fermions are protected by a chiral symmetry, while the mass of scalars are not protected by a chiral symmetry. So there is no symmetry that protects the mass of a scalar. And so The mass of the Higgs, being of this kind, is not protected by any symmetry in the standard model like in any other theory, and so it can receive large corrections, which is totally fine, but the question then becomes why it has the value it has. So why, by the sum of different terms that are in principle as large as I want, finite but big, at the end I get a mass that is of the order of 100 GeV. So this is something that I brought, for instance, a lot of different BSM extensions to be very auspicable, like, for instance, supersymmetry, in which the cancellation is exact if the symmetry is exact, and therefore there is contributions by different super partners that have both, they differ by one half of spin between one and the other, cancel exactly in any loop corrections. Of course, it's not the case because the symmetry is not exact, so we have not really solved the problem, but is one of the reasons why we are looking to BSM models as a possible explanation for the realization of the electroweak scale at the value which you have. So this is what we also call normally the naturalness problem. Now, you can also take the point of view of saying, I don't care. So you can also take the point of view of saying, I'm fine with the mass having the value that it has and being fine-tuned to that value by the cancellation of large terms and live with that. But it's an indication of something that needs to be thought about. As the coupling to fermions that I had pointed here is an indication of something that has to be thought about. So after all this explanation, I wanted, and after having tried to motivate to you why we really need to go deeper into the Higgs sector, and why we think, if you want, you can take the point of view of saying, yes, the Higgs has completed the standard model. In a way, it was expected, but at the same time, it's something that maybe it's the first real signal of physics beyond the standard model, because it's something that is so weird in a way and so ad hoc that cannot really be the end of the story. So we need to use it. It's our handle to something that is beyond the standard model. And the hope is just that by doing Higgs precision physics, we will have a preferred avenue towards the whatever we know that has to exist for the multitude of problems that you have heard about that still do not have an explanation in the standard model. And before looking finally at these machines that we're talking about, let me just give you, I always like to give a couple of examples in which we really see why history can teach us something, right? We don't have to live out of history. It's good sometimes to put history behind us and move on and be bold, right? But also knowing something of how our field has evolved can be very, very interesting. And there are two examples in which these, if you want, continue dialogue and complementarity between precisions and energy have really moved us forward and have demonstrated the strength and the power of this dialogue. And they're related to both if you want, the story of the top quark and the story of the Higgs itself, right? In which you really see how we went from precision to discovery to precision again. And the new precision has led to another discovery. And so now it's time to go to precision and maybe discovery again. That would be great, right? So this is why I wanted to, sorry, going too fast. I wanted to show you. Page down. Like, and I want to go to the next one. Okay. So this we looked at yesterday. This one. Okay, thank you. So this is, I say top right there, right? And this is a plot that I like to show, in particular to young people like you, right? Because look at the plot on the left-hand side. This is a plot that Chris Quigg, a great physicist of our time and one of the best pedagogues that I ever met, right, has put together, and sure enough, he has put together something that is really interesting. He put it together a while ago because the top was discovered a while ago, right? But what this is showing to you is really, so see, it starts back in the 1990, and then it goes on. So the top was discovered here. So all these determination, the green dots, are indirect fits. So this is precision. And this is precision coming from flavor physics, mainly, right? So in my scientific history, I was right here, right? So just before the discovery of the top, working on flavor physics, as a matter of fact. And when I look back at my PhD work, my PhD thesis, I have plots in which, coming from K-on and B physics, in which we had the value of the top of the mass between 160 and 180. Not bad, not bad, right? Okay, so and this was really here, before the top was discovered. So you see how precision physics, in this case flavor physics, had kind of gone better and better and better in precision, and closer because of more accuracy in the predictions, understanding more processes that also could be measured not only on K-on physics, but also on B physics, very sensitive to indirect effect of the tops, quantum effect of the top, loops of tops, right? And finally, the top was discovered, and it was discovered pretty much where it was predicted. I told you the values that we had in our plots. And then, of course, the moment in which it's discovered, well, you measure the mass, right, because you produce it. And so, of course, the precision becomes better and better and better and better, and these are the years of the tevatron. And if this plot could be extended, maybe we took the time at some point to extend it, we will see the impact of the LHC coming in there. And the LHC at the moment is basically doing comparably, if not better, than the tevatron already. So the LHC will be out here, right? So here is really a situation in which you see going from precision physics to discovery. And then there is the whole story of the LHC. So here you see the comparison between measurement of the two main LHC experiment, Atlas and CMS, of the mass of the top, at the different energies. So if you look at here, you will see the measurement that were done at 7 TeV and 8 TeV, and the measurement that are now done at 13 and 13.6 TeV that are up here. So all the different phases of the LHC, run 1, run 2, and run 3 now, but these are probably data just from run 2. And so you see both of the experimental little dots and the theory prediction. And the theory prediction these days is very, very precise. So it's a theory prediction that includes 2 orders of quantum corrections. This is what the NNLO means. So we will discuss these in our lectures more precisely what it means, but probably you already know. Or in any case, you can take my word for true for the moment that these are 2 orders, so 2 loops and 2 orders of radiation in the cross sections, plus a resummation of large corrections. So you see the kind of precision that has been reached in measuring and predicting the mass of the top. There are still discussion ongoing. There is still room for improvement. It's not done, but you can really see the continuation of this plot down here, right? And in the one on the right, where you see the actual measurement in all possible different measurements that the LHC can do, TT-bar production, exclusive productions, and et cetera, et cetera. And this goes back to the fact how many things we can measure at colliders, right? And how much we can understand. And of course, this fits back into flavor physics that is up here, right? It fits back by helping now understanding other things in flavor physics. So here, a first example of really precision that fits into discovery, and then that discovery that then allows you to have something that you have control of, and you can measure the properties of, and you can measure them more and more precisely and use it to discover something else, which is indeed what came next, which is the Higgs. And here you see this is LHC time, this is LHC physics. The top has been discovered. The measurement of the tevatron has become more and more precise. The top mass here can use as an input, right? And here you see the value of the top mass and the corresponding ellipses that have become smaller and smaller, to the point going from, you see, LEP1 and SLD. These are names that are meaningful to you after our discussion yesterday. These were the plus and minus colliders that were working in the late 80s and 90s that gave us both a measurement, that gave us a measurement of the mass of the W. Now the tevatron comes in, and of course the tevatron has a big impact because it measures the top. Right, it discovers the top and it measures the mass of the top, and you look at how you go from these very large areas to this very tiny area in this two-parameter plot. And then the bands here in yellow and green is for this value of MW and M top, what is the predicted mass of the Higgs before discovery. And this time here, if you look at the date here, is before the Higgs discovery, right? And if you see, the consistency of the model is down to almost nothing, right? If you take it at the 1 sigma, right? If you take it at a little bit more, so it's really, there is this tiny region in which you would have to find the Higgs. And sure enough, there is where it was found, to the point that it was almost excluded, right? So this is, again, a history of precision. So you've seen the top being predicted by flavor physics, discovered, and then measured more and more precisely, and then used for the next step. And now the Higgs that has been discovered, we don't understand what it is, but we can measure its property. We can measure its mass, and here you have an example, just a summary of all the measurement of round 1 and round 2 of the LHC in all the possible different usable channels for such precision measurement. And then you see how this feeds into an updated version of this plot, where you don't have the yellow-green band anymore, because now you know where the Higgs is. You have discovered, you can measure its mass. And so here it's hidden in the fit itself. What this fit is a precision fit of the standard model, which means that you take a bunch of the most precisely measured properties of the Z, the W, the Higgs, including its mass itself, and at the moment not its couplings, because they're not measured precisely enough to make a difference in a plot of this kind. And you then look at the correlation among them, and if there is any stress between two of them, because they're all related through the quantum structure of the standard model. So the moment in which you take the mass of the top, the mass of the W, the mass of the Higgs, you calculate the kind of loop corrections that we saw before, you renormalize the theory, they get related one to the other through quantum effects. And so you can really build a stress, if you want to test a combined global fit, how we call, of the standard model, and see which kind of effect you have when you fit the model without, for instance, MW and top, or with, and you have a large region of this parameter space that is available, how it gets constraints by using them, by using your precision measurement. And as I was saying, the Higgs is hidden in here with its value and its error. And how it can be even more constrained if you go to a more precise machine, because with higher statistics, which is that the high luminosity LHC shrinks even farther. And I haven't brought this up here because it will open a new discussion that we are going to have when we look at specific how that is measured. But you may remember the commotion that arose in our field when a new value, a new measurement of the mass of the W came in about a year and a half ago, right? Almost 2 years by now. That looked a little bit off chart. Right? So it looked a little bit in real tension, but with a very small error compared to the average that was there since then. Well, if you had to look, and we will look at them at plots like this, you will see a huge effect. So you will see how these bubbles get pushed off what are the experimental measurement of M top and MW if something like that comes in. And when you look at the numbers, they were not terrible, but when something is measured really precisely, it can become a huge error. So things like these are very important. And we now hope that with the precision measurement of the Higgs that are not included in these yet, right? Because except for the mass, that's the only thing that is included, but the couplings are not, because we will learn more. We can do global fits that are more global and include the kind of physics of which we understand the least. So the hope is just that this pattern of precision discovery gets repeated. And that's precisely the logic that we are following here in say, let's go for more precision. Well, sorry, this is just for direct. Let's go for more precision. Let's go for more energy. So let's push this vertical line farther, and let's push this diagonal line down to exclude more and more of the parameter space that we are considering. So finally, how are we planning to do that? I wanted just to give you a list of options that we have out there, none of which is real for the moment. They're all proposals, but they are proposals that are under serious scrutiny by the community, right? And the community means many things, right? So this is, it's in the slides, so it repeats what I've tried to sketch there. I figured that I will put it in my slides because it's better drawn here, so it's more readable, but I also have my hand version in my notes, so you can look at both. And so I took these from the exercise that I talked to you about, this NOMAS exercise, and you take it as just not anything that is what will happen, right? So it's just a list of possible scenarios that we have, and a list of possible future collider that we have considered in this study, because they were at a level of development such that the parameters of the machine had been seriously studied, and the physics of this machine had been decently explored, right, I would say. So here is the division that I was talking about, so what we call Higgs boson factories below 1 TeV or up to 1 TeV, and here is what we call multi-TeV colliders above 1 TeV center of mass energy. Now, remember that the center of mass energy is not necessarily the parton center of mass energy, so things that have 100 TeV and RPP collider can be comparable to things that have maybe 10, 30 TeV and are lepton collider. So as I was telling you, on this side, well, we also listed the high luminosity LHC because the center of mass energy for this machine, as we have discussed, is not much more than 1 TeV, right? In spite of the 13 TeV total energy, because it's a PP machine. All the others are a plus and minus machine. They are linear collider, like the ILC or this C-cube proposal that came during SNOMAS. And the C-cube stands for cool copper collider, because it's a collider made of copper that is cooled to very low temperatures. And then CLIC, which is, has a phase as 380 GeV. The many energies that you see, for instance, for the ILC, this international linear collider, are due to different kind of physics that can be done there. So physics that can be done at the threshold of a little bit above WW production, and energies that is very similar to what LEP2 had at the end of his story. And then TT bar production, and then you go up to a 500 GeV that should be better pushed to a little bit higher than that if you wanted to do top physics. And finally, 1 TeV as the top energy. These days that they're talking even about a little bit more than that. And then CLIC, that appears both on the left and on the right. It has a low energy phase against the basically TT bar threshold, and here, so the threshold for producing a pair of tops, and here going to higher energy, 1.5 TeV and 3 TeV. So this is a machine that, being a lepton machine, a plus and minus machine at such high energy, if realizable, can be a discovery machine. And so this is why it is listed seriously under a multi-TeV collider, because it's a very clean environment. So this is all energy that you have available to produce at that level of particles, right? So particles that have very high mass, and to see them well. And then you have the two machines that are circular colliders, E plus and minus machine, the FCC version EE, so E plus and minus, and the corresponding machine proposed by the Chinese community. As you see, they have energies that go very much in parallel, and here they're written specifically in terms of what they will do. They will sit on the resonance of the Z, so do a superlap, right, if you want a superlap one. So sit on the resonance of the Z and measure the properties of the Z boson at extreme precision. They will have a phase that is called giga Z, so a phase that is billions of Z produced and studied. Then they will sit at the threshold for producing 2 Ws that open new possibility for the production for the study of electroweak interactions and in particular diboson production. And then they will go up to W top and to top productions in the order. And as last among the Higgs factories, you see a muon collider in a phase that, if you pay attention, sits on the resonance of the Higgs. So you see, that's 125 GeV is the mass of the Higgs. So this is the idea, basically, of doing what LEP did for the Z for the Higgs. Just sit on the resonance. When you sit on resonance of something, you get the enhancement of sitting on the resonance of a particle. So you have you're sitting in the mass distribution, in the energy distribution. You're sitting really where the particle is produced. So you get a lot of them. And so you can study with a huge statistic the properties of this particle. Actually, this is not the option of the muon collider that has been most pushed. It's very different. If you now look at the multi-TeV collider, you will see the muon collider coming in again, but with a center of mass energy much larger, of 3 TeV and 10 TeV. We will have time to probably later to discuss that why these two machines are very different from one the other, apart from the size, but also from the kind of things, as we were discussing yesterday, the technology is very much under development, and the kind of things that need to be studied in the two cases are very different. And because of the fact that this can be an incredible discovery machine, people are more interested in this one than not in the other one. So the benefits of this one will be probably well compensated by having an E plus E minus machine doing precision physics. The benefit of this one is comparable to a 100 TeV PP collider. That would be the age phase of the FCC. And at the same time, it will be complementary because it's not the same machine. So as you may imagine, this is a machine that collides protons. So protons are composite objects. They are very strongly affected by strong interactions for the good and for the bad, as we said yesterday. And so you will have the possibility of doing a kind of physics that a mu plus mu minus collider you cannot do with the lepton initial state. At the same time, the mu plus mu minus collider will be much cleaner because it doesn't have all these strong interactions in the initial state, and therefore you will be able to have easier access to processes that may be kind of polluted or hidden at a PP collider with such an incredible center of mass energy that also will boost all the hadronic activity present. So this is just, I listed in the bibliography that I also posted or sent for posting a couple of references that you can look up if you are interested in more technical details for these machines. For colliders in general, there is a nice review of present and future colliders that also lists for you the principles on which any collider machine is based. And I think it's very beneficial, even for theorists, just to know which kind of things need to be considered beyond the very elementary things that I've introduced for you yesterday. And then there is, I posted the reference to these, I posted the link to these reference here that came out of the Snowman study, and it was the result of a task force dedicated to the study of all the specifics of these kind of machines. And so in there you will find all kind of details, from geometrical details to energy details to power consumption details to environmental impact of these machines. So all kind of things that you may be interested on, organized in nice tables and charts, comparisons, and etc. And this is actually what is being used. So this is what is being used for big decisions. So for decisions that not only are based on the physics that we are discussing here, but on many other considerations that are not necessarily less important, right? Because physics is one of the components of our world and of our society, right? So it's not the only thing, right? So, but what SNOMAS did, as well as the European strategy, as well as other studies that are going on in other parts of the world, is just to provide the physics to the decision makers. So to people that then will balance a lot of other things in figuring out what is the best for our community and for the world in general. Of course, there will be also an economical component to that because these machines cost money, which is probably nothing compared to other expenses. But still, you have we are sort of if you want something that is not perceived as absolutely necessary to the survival of humanity. So that's that we have to take that into account as well. Okay, so I think I wanted to complete our discussion, the discussion that we started yesterday, because this gives to you somehow the motivation the big picture. So why are we doing collider physics? What are we talking about here? What have we done so far? How have we probed and validated the theory that we have so far, which is the standard model? And how have we probed and explored a wealth of other ideas that have come up and that are fascinating and maybe true also, right, to some extent. But and how we have developed a science that is very powerful in constraining any existing or future idea that will push us forward into the understanding of the true elementary constituents of our world and their interaction. Now, from now on, we kind of go more into the crux of the matter. So we just let's say, okay, this is all nice and I'm really excited about all these, but how do we do that? So as in particular from the theory point of view, how do we really provide the predictions and come up with predictions that then we can compare with collider data, because this is how we are going to use the wealth of measurement that I have emphasized for you in this presentation. And so for that, I would like to really start, I was thinking about how to say it in a few words. Well, the fundamental thing that we have to keep in mind and face from the very beginning is just that the goal is for us theorists, and in particular for as a theorist doing phenomenology, so wanted to come up with predictions that then are compared to collider measurements, is just to face the complexity of collider events. So collider events are really nasty beasts, right? They're really complex, right? If you have ever seen the picture of a collider event, the first reaction is just that there is no hope that I can predict anything like that. There is no hope that I can get anything out of an event like that. You see these zillions of tracks going all over the place, and say, what, right? It's just a piece of art, or is really something of which I have to make sense of, right? Still, then you see measurement at the percent level. So something has to happen in between. And I think it's really fascinating to dig in and really understand how we make sense of this big, complex problem. Now, the complexity is both on the experimental side, and I will say very little about this because, as I disclaimed at the very beginning, I'm not an experimentalist, so I cannot really guide you through the gory details of how. But just to give an idea of what is out there. So the LHC, which is not yet the high luminosity LHC, but just the LHC as it is right now, I collects a number of events per second that is mind-boggling, so the order of the billion, right? So the order of 10 to the 9 events per second. So those each event requires a certain should be recorded, and I'm talking just on the difficulty on the experimental side. In order to be an event, right? So to have the images that you see should be recorded. It takes space to record it of the order of the megabytes per event, and you have to compare that to the CPU speed of your computers and to the storage space of your computers. So it's clearly not possible to record of the order of 10 to the 9 events per second, each one of which takes, so gigahertz is more or less the clocking of your CPUs, right? And it's impossible, right? So so there is a lot of screening that has to be done on the spot, right? While events are being generated in order to decide if an event is kept or not. You have to reduce that number by a lot. So you have to reduce that to the order of 100, 200 events per second. So you go from billions to 100, 200 events. So most of actually what is happening is lost, right? And this is the famous job of the triggers that the experiments have. And some of you are experimentalists, so they probably have been working on it, and they know much more than I do on the gory details of how to do that. But for theorists in general, just remember that a lot of what comes in is dropped right away. And you have to have a very efficient way of, so a very efficient criteria and different levels of criteria that are applied in order to drop these events. So you need to know, more or less, the kind of events that you are looking for, which is, there is where the theory comes in, because luckily enough, we have a theory, which is the standard model, that is telling us a lot of what to expect in first approximation, unless there is some striking new physics event that we haven't seen yet, right? But in first approximation, it's telling you what is the bare bone of the solid ground on which we should expect which kind of particles to come out. We will expect leptons, electrons, muons, strong interacting particles coming out. We know the nature of QCD, and this is something that we are going to discuss together. So given the nature of the theory of strong interaction at high energies, we know that we will see at the collision will be among the constituents of the hadrons, and we know the shape that hadronic activity will have in coming out of the collision event, what we call jets, right? So we know all these things that we see in more details. So at the first level, we will start to eliminate anything that does not have any of these characteristics. Not because it's necessarily uninteresting, but because we are looking for events that then we can really spot, we can really understand better. And so one important thing is just that to remind ourselves is just that from what we discussed yesterday, so remember that the colliding beams are coming in opposite directions, right? And most of the activity is on the axis of the collision. So a lot of the fuzziness and mess will also be close to the beam. And for hadron colliders in particular, we do not really know what is the energy in the center of mass. So we have this unknown because we have fractions, right? So what we can do, however, one thing that we know is just that there is nothing to start with in the transverse direction. So if we look for events that have large PTs, so they have large momentum in the transverse direction, we have much more control. So these kind of concepts are used to drop a lot of the events that are not hard enough, for instance. So if you look at the different trigger levels that are used experimentally, there are trigger levels in which you select high PT leptons, in which you select high PT jets, all these kind of things, right? And the rest, it's not that it's not interesting, it's less usable in a way. So having to make choices, you would just like to keep, having to drop something, you would like to keep what is most easily to work with. That's basically the idea. So I'm not gonna really tell you much more than this, but just what I wanted to suggest to you is just that the fact that this is what is happening on the experimental side, that it's very important to have a good idea of what the shape of events are in the standard model, because first of all, you know which events are more easily to use, as I just said. You also know that if something, you can also decide at some point to put into your trigger a criterion that says if something is really anomalous, keep it. But you have to know what anomalous means, right? So you have to know what something that is really impossible in the standard model has come in. So the knowledge of the dialogue between theory and experiment in this case is very important. And it's not unusual that trigger selection have been implemented to satisfy certain theory searches, right? It's something that is sometimes not easy, as none of the dialogues between experiments like the LHC experiment that are huge experiments in which a large community of people is involved. And decisions have to go through several levels. It's not the decision of one person. It's a decision of a group of persons working on something at multiple levels. So it's not easy to come as a theorist and say, oh, I have this idea, you should change your trigger to do this. It's not going to happen like that, right? So, but it can, at some point, if an idea is solid, if there is a good reason, if you get the right time frame, and maybe the new trigger decision has not just gone in the day before, for which you have to wait another couple of years before there is another one. For a lot of different things, there is this dialogue can happen, okay? Now, this is for the experimental side. For the theoretical side, and this is what we, I think we have about 10 minutes, so it's nice to end with this picture. That is the introduction to what we are going to do, right? So what does a collider event look like for us, right? So we look at the picture, it's a total mess, but now we have a theory, we have the standard model, right? And the standard model is telling us some principles that we can use in order to kind of clear some of the fog that is around these events and look at the bare bones structure of the events from a theoretical point of view, right? So if we think to LHC event, and I'm starting, you can tell me, why don't you start with any plus and minus machine that is much simpler? Well, because the PP event, so the LHC events, being more complex, are also more interesting from the point of view of saying how, as theorists, we look at a collider event. And we know that if we understand those, we all understand that they plus and minus. So in the picture that I'm going to put on the blackboard, you will see the case of hadron interactions, so the case of hadronic scattering. And of course, it would be enough to drop some of the complexity to reduce to the case of E plus and minus interactions. So in this picture, so you have two beams of particles coming in. So you have proton-proton colliding at a collider at a colliding spot. So let's see if I can have a similar drawing in my notes. So you have your proton coming in with their energy. And protons, we know they're made of many constituents. They're made of partons, right? So you may have seen or not the parton model, but the basic idea is just that the proton, you see it as collections of constituents, partons that carry a fraction of the momentum of the proton. So now, some of them, and in particular, here we single one of them, will enter a hard scattering that I represent here. So there will be a parton coming from one of the protons and another parton coming from the other proton that is entering a hard scattering. Hard is hard in energy, so it's a high energy scattering. And why at high energy we can talk about parton scattering? So this is a parton. This is a proton. So this can be a quark, an anti-quark, or a gluon, and the same on this side. Why we can say that is just because at high energy, and this is where our theoretical knowledge comes in, we know that strong interactions are described by QCD. And QCD is telling us that through the properties, through the asymptotic freedom of the theory, that the strong couplings is weak at high energies. So at high energies, I don't see the proton as a bound state. At high energy, I start seeing the constituents. So when these two objects come together at really high energies, their constituents are free. And they can see each other. We don't see them coming out. By the time they come out, they have already reached an energy for which they're bound states again. But at the collision at high energies, they're free particles. So free from the point of view, free from the binding of the proton. Then they interact, right? So this, we are sure about that. Now, once the hard scattering will have an initial state, which is this one, and we'll have a final state. So there will be objects coming out that are either quark or anti-quarks, or let me draw, as always, the gluon as a spiral, and also other things. There can be leptons too coming out because it depends on which kind of interactions. The quarks also interact electromagnetically, of course, and they interact also weak. Of course, there is a hierarchy of interactions there, but I can expect that whatever comes out of here, some of which will be also quark partons, that then they come out at high energy, but then by future emissions, they go through a chains of further radiation and lower their energy more and more till they get to an energy in which QCD, strong interaction, starts being strong again. And so they reach a phase in which the individual partons, they hadronize again. So this phase, let's put it out here, right? It's a phase in which hadronization happens. And here I can see, again, I don't know, kaons and B quark and pions and whatever else being formed together with photons, electrons, and muons that are coming out of the scattering process that I have here. So there will be things that go like straight out here and are not strongly interacting, and there will be things that, on the other hand, along the way, will keep radiating and at the end, by the time they're here, just bind up into hadrons, into the hadronization phase. And I can dress up this picture as much as I want with this kind of radiation that keeps going. So what do we understand of this big picture, right? And how do we go in calculating a cross-section, for instance, for a proton-proton into some final state F, plus that we wanted to pin down, plus anything else that is coming up. So how do we go calculating this cross-section, both at the total level and also at the differential level, right? So we see it together starting tomorrow, but what I wanted to tell you today, and then keep this picture in mind, is just that as we justified. So first of all, the most important part of the story that we needed to start discussing first is really the strong interaction part. So it's really QCD, the QCD part of the story, because it's the LHC is a proton-proton collider, and that is 80% of the story that we needed to understand. Then, of course, on top of that, there is also the rest of the standard model that we will also discuss, some of which have similar characteristics, some of which have not. But once we know and we can handle what happens with the strong interacting part of the story, we can probably understand the rest as well. If this had to be an E plus E minus collider, of course this part would not be there. So we would only have the E plus and the E minus coming in, and our life would be much easier. Here, what we can already dissect is that there is this hard scattering, and then we have to discuss that is happening at the parton level. And we have, however, to connect to two regimes, an initial one in which the partons are bound into the protons, and a final one in which this parton level process has evolved and then bound up again into other hadrons, in which we know the strong interactions are non-perturbative, right? So if I have to distinguish what is perturbative, and perturbative means we can calculate it, and what is non-perturbative means that we have to find a way to figure out either how to get it or why it's not important to get it. So it's just that there are two different things. Well, I would say that here definitely, when the partons are bound into the proton, this is non-perturbative. So there is a non-perturbative. So let me call it N non-PQCD, so non-perturbative QCD. Here, at the level of hadronization, this is non-perturbative QCD effects. But in going from the non-perturbative, from the scale, that is the scale of QCD, so the famous lambda QCD. So this is the scale of energy in which this happens. When you reach this scale of energy, you switch to the non-perturbative phase. In going from the hard scattering back to the non-perturbative bound state of partons, and in going from the hard scattering towards the non-perturbative phase of QCD, This evolution can be calculated perturbatively. So going from the Q scale of the hard scattering back to the scale of lambda QCD where partons are bound. So this evolution and this evolution, of course, with due care, so spelling out what the rules of the game are, so the kind of approximations that you do in doing these, and therefore being aware of the kind of errors that you may make in doing that, but the evolution in both directions can be algorithmically spelled out perturbatively, using perturbative QCD. So these in the red, everything is perturbative QCD, and we can calculate it. And we will see how to calculate it, because both in this direction and in that direction, our approach is universal. So it doesn't depend on what is happening here. It doesn't depend on which kind of process I'm looking at. It's the same for all kinds of processes that start with the scattering of quark and gluons and go back to the protons, or go forward to hadronizing into other bound states of mesons and baryons, so other bound states of partons into hadrons. So what we're going to do together starting tomorrow is just to really calculate these structures to see what goes, why we can, first of all, factorize our problem this way. And this is due just to the difference in energy between the two that also correspond to different time scales in which these effects are important. One proportional to 1 over Q, and the other proportional to 1 over lambda QCD. So one is much faster, the other is much slower. So the non-perturbative effects kick in much after the hard scattering. And that's the reason why we can factorize them and calculate things as a hard scattering cross-section evolved back to meet the probability to finding certain partons into the proton that we call parton distribution functions. So in this evolution, we will talk about parton distribution functions in here. And we will talk about how we go from the hard scattering process to the low energy scales of hadronization with something equally universal that we call parton shower. We will see that the crucial thing that we need to discuss is the nature of QCD radiation at the hard scale. And once we understand the nature of QCD radiation, so what is the shape of QCD radiation here, and what is the universality of QCD radiation at this, in this central element, we will be able to iterate it to both build the parton distribution functions evolution and the parton shower evolution. So there is a big component of universality in this discussion, which is the power of it, and there is a component of specificity that is all in the hard scattering process that we can calculate in perturbative QCD. And if we want, we can add to that a QED correction, we can add to that electroweak corrections, and so on, and make it more and more precise. So after we have developed this full picture, we will then look, probably in the last 1.5 lectures, to specific cases when this is applied. So cases of Higgs productions or top production of other things, and understand where they play a role. Okay?
Questions?
Okay, thank you for the lecture. It was really interesting. I have a couple of questions. I'm going to say some here and maybe some later. Mm-hmm. But when you talked about how we, in hadron colliders, we usually use mainly transverse momentum because that's what we are mostly sure that it is expected to be zero.
Well, because you know your starting point. So you know that to start with is zero.
Yeah.
Right? And so you have a balance. So even if you, because sometimes you don't see things.
Yeah.
Right?
Exactly.
But when you don't see things, you saw how much you don't see. Then that's part of the...
But so in, for example, in lepton colliders, can you use the information of the longitudinal momentum because we don't use that in hadron colliders because it would be a statistical nightmare to try and work it out.
There is another important point that the transverse observables are also boosted invariant. And because in a hadron collider you are boosted, because you have a longitudinal component, those are frame independent. At a lepton collider you could, if there is still the issue that they may be, if you want, less clean in any case because they're closer to the beam direction, right? So they're more subject to radiation, right?
But are they used like in LEP or other colliders? Is this information used? Or
sometimes.
Okay.
Yeah.
Maybe, and also just to confirm, I think you said it, but I didn't hear it. The trigger settings are constant throughout the whole run of experiments. Like you define them early in the run, and then it's the constant throughout.
They are updated from time to time. They're not cast in stone for 20 years, so they change, right? Yeah. Much more often. Not every day, right? So it's a process. I mean, there are a lot of trigger studies continuously ongoing, not just induced only by theorists, induced by their own problems as well, right? I don't really know now exactly what is the schedule of that, but I have witnessed several times a discussion on let's propose this, let's propose that. So I have the impression that they are updated from time to time, right? I mean, of course, you have to imagine that this takes a huge software development to do this kind. Part of the triggering is really hardware, but part of the triggering is software.
Yeah, so starting it's customizable.
I think starting from the next to the base level to the level 0, I think Atlas call it a level 1 CMS, I don't remember, but past the first really basic level is mainly software, right? So updating anything like this is a huge thing, right? But it's done, right? So.
Okay, thank you.
Okay, I don't see any more questions. We'll have the Q&A in half an hour anyway, soon. So let's thank Laura again. And we'll reconvene at 5.